So the strength of the London forces, which is also called dispersion, induced dipole, and van der Waals forces, you'll see all those words, so you need to be familiar with all of them to describe. Dispersion, I think, is probably the next most common word used to describe this type of force. But the strength depends on also depends on the molar mass of the compound. Okay, so what you see with the London forces in the nonpolar compounds, that the more electrons you have, the bigger the mass, the more electrons you have, the more of this type of force you're going to see existing. And so with these forces, the bigger the molecule, the stronger the London forces are going to be. You can tell by looking at the differences in these three molecules: pentane versus pentadecane versus octadecane. So that's, pentane would be 5 carbons, pentadecane would be 15 carbons, and octadecane would be 18 carbons in a hydrocarbon. And that's what's pictured here. None of them are polar. They're all nonpolar. The only difference is how many carbons they have, and therefore the extent of the molar mass. The shapes are the same. They're all just long hydrocarbons. And this is the octadecane. It's actually a solid at room temperature and pressure. Okay, and you can see the pentadecane is kind of oily. That's an oil drip off of here. And the pentane is very similar to the hexane that you guys have experienced already in class. It's just a very volatile liquid. Okay, and so the strength also depends, in the case of the dispersion, on the shape of the molecule. All right, if you have a kind of a long molecule that can have lots of places for dispersion to occur, you're going to have more opportunities for that molecule to have forces existing, and so you would expect that it would have a stronger attractive force and therefore higher melting point and boiling point. If your molecule is kind of a circle or a ball kind of rolled up kind of a deal, then less opportunity for overlap. You would expect the molecules to be weaker. So it depends on the shape also. So it depends on how big it is and the shape. And I like to have people think of Velcro when they think of these dispersion forces being additive. You think of a kid with a little baby shoe that has just like a little piece of Velcro on it, and a child's hand, which isn't very strong, can very easily pull the little pieces of Velcro. And Velcro's, there's like a hook. It's just like a hook and a hook and a hook and a loop and a hook and a loop and a hook and a loop. That's how Velcro stays together. Imagine hook, loop, hook, loop. So if you're trying to use this analogy for dispersion forces, the more hooks and loops you have, the more opportunity for these little forces to add up. All right, so a child's shoe would have less hooks and loops, and so it'd be easier to pull it off, pull off that piece of Velcro to open the shoe. Or imagine, you're wearing a whole Velcro suit and you're going to go throw yourself against the Velcro wall. Have you ever seen one of those? Okay, a person running, towards the Velcro wall, all those hooks and loops that are on that suit can hold that person to the wall. Okay, so the bigger the molecule is, the more opportunity for these dispersion forces, the more polarizable it is, and that's why we can see, nonpolar solids. All of these individual dispersive forces are adding up to actually allow the thing to be in a solid, even though the molecule itself isn't polar. And that's when you think of your petroleum products, all the way from asphalt up to the gases. It just depends on how big, how massive those molecules are, how many opportunities they have for inducing dipole moments. So, so we see, like, for example, that the big nonpolar molecules can exist as solids, no problem, at room temperature and pressure, and even higher, due to even higher temperatures because of this additive force. So even though we say that the London forces are the weakest type, they are additive. So if you're just comparing, the same molecular weight, and you have an opportunity for a dipole-dipole, of course that's going to be stronger. But if you get a much, much bigger molecule, you're going to see that the dispersive forces add up, and they will have different physical properties than what you might expect.